Thanks, last time, we started talking about distribution and density of the sum of two random variables or more that are independent. And we went through the derivation, and we found that the density of the PDF of sum of two random variables, W, which is x plus y, where x and y are independent, is equal to the combination of the PDF of x with the PDF of y. Okay? And went through the derivation from the start of the definition of the CDF, and by finding the region at which we need to integrate these joint PDF. And we went through the example, and we stopped here. So today, inshallah, we'll continue with the example, and then we'll talk about the central unit theorem, and this will conclude chapter 1. The next time, inshallah, we'll start. Okay, so we started with basically the example was we had two uniform random variables with PDFs. The first one for x between 0 and a, and for y it's uniform between 0 and b, and accordingly the density is drawn accordingly. Now we are interested in finding the PDF of W, which is the sum of the two random variables. Okay, so and we stopped at this. Talk about the difference between the PDF of W and the joint PDF. The PDF of W is the convolution between the PDF of x and y. W here is the sum. The W is the single value. The single value. While the joint PDF of x and y here, this is the joint PDF between x and y, which is because they are independent. It's basically equal to the PDF of x multiplied by the PDF. Here, this is a function of x and y because it's a function. It's a joint PDF. While W here, the FFW is a function of W because it's a single value. We need to distinguish between the two systems. Okay, and the way we do it is we need to simply convolve this PDF with this PDF. Okay. Now, in order to do the convolution, you can have the graphical convolution, or you can transform into Fourier or series, Fourier transform or using the Laplace transform, or you can do it directly. So let's talk about the graphical first of all. Graphical convolution. First of all, the convolution. What is it? What is convolution? It's you take one of them and you multiply it by the other after flipping and shifting, right? So basically, you take, for example, fx, you flip it and you shift it. So, for example, if we take this as it is and take fy, we flip it and we start shifting it. We shift by w, and every time we multiply. So when when we flip this, it starts from minus b to 0, right? Okay, and so for w before 0, before we reach 0, what is the product of this multiplied by this? It will be 0. So everything before 0 is 0. Now, once you start crossing the 0, so w becomes more than 0, then this multiplied by this will be the common factor, right? And it will increase linearly as w keeps increasing. So I'm talking about shift. Talking about this one when you shift it and slide it. So this will be w, and this will be w minus b. Okay. Now, when w equals 0, before 0, as I mentioned, the product of this with this is 0. Once it crosses 0 and w keeps increasing, the product of this with this is positive, which is equal to 1 over a multiplied by 1 over b, and it increases linearly as w increases. So as w increases, it keeps increasing linearly until it reaches the maximum. Okay, and then when w, so basically this is when w between 0 and a. Now, when w crosses the a, what happens? هتبدا تتحرك كده. What happens? Up to B. The area between, yes, the common factor, the area اللي هي هنا مع هذه هتكون constant. So basically between A and B there will be no increase. The area will be the same square, the same common factor. And once you cross B, once you exceed B, the area, the product between them becomes smaller and smaller. And this becomes decaying factor until you reach A plus B. At A plus B, the common factor will be 0 and you graphical condition. You've taken it somewhere in procedure, right? So this is one way. The other way is to know that you have convolution can be taken into, for example, into Laplace transform. So this is Laplace transform. Okay. When you have convolution in certain domain and you take the Laplace transform, what do you get? Multiplication. What is the Laplace transform of f of the PDF? Did that correspond? Characteristic function time is Fourier transform. Laplace transform was the moment generating function. ما تقدر تستخدم بول او اي واحد منهم. الفكره كالتالي. Convolution in the PDF domain will be product in the characteristic function domain or the moment generating function domain. Okay? So basically if W of W can be found by converting the PDF of X and Y, or by finding the moment generating function of W of Y, moment generating function of X, which is this multiplied by this. Okay? Multiplying them will give you the product of them. Now taking the inverse Fourier transform, the inverse Laplace transform, inverse, gives you FW. Okay? Okay? So again, FW of W is the convolution between the two PDFs of X and Y. Now, one way to find the convolution is to go to the transform domain, which is when you take the Laplace transform of Fy will give you the moment generating function of Y. Taking the Laplace transform of Fx will give you the moment generating function of X. Multiplying them, now you have a new function. Now this is the moment generating function of W. So taking the inverse Laplace transform will give you the PDF. Okay? So now, for example, here, fx can be written in terms of this, which is u of x minus u of x minus a. Remember, fx was what? Was this. So it's 0 before 0, and then u of x multiplied by 1 over n, which is a step function. Right? Step function continues forever. However, at a, we take minus again, another step function of the same magnitude at a. So this gives you u of x minus u of x minus a, multiplied by 1. Similarly, the PDF of a of y can be written in terms of u of y multiplied by 1 over b minus u of y minus b. Okay? Now, taking the Laplace transform of these two, the Laplace transform of this will give you 1 minus e to minus as divided by as. Check it out. And the Laplace transform of this will give you this. Now, multiplying them together will give you the Laplace transform of the PDF of y, of the relation. Inverse, taking the inverse of that will give you the PDF. Both of them should give you the same answer. So whether this or this will give you the same answer. At the end, it's the same function. It's a different approach. So, Again, all of this is because you know how to do combination, you know how to do that, so on. If you don't know, you will have problems. So يا شباب please review this يعني you need to master it. يعني حرام يا اخي شيء تخطئ في سؤال just because you don't know how to do combination, which is another course ما له علاقة فيه. Okay. طبعا again زي ما قلنا الابتدائي usual exams here will not be so will not test you on 207. You will not try to challenge you on 207 calculus. But still you need to do it. You need to know a couple of these.
But when I start with the
No, you need to read what you need to understand what. لازم تفهم ليش الثنتين موجودات why they exist and how to do it. What. يعني ممكن اسالك اقول لك do it for me using graphical calculation. بشوف تسوي. ممكن اسال لك يعني انت شوف مثلا هنا in this particular example انا I see because the functions are nice and constant and so on it's much easier to do it using graphical. لكن اعطيك function ثاني معقد x squared ولا e minus x ولا شيء it will be easier to go using Laplace transform.
How can I get the value of W, say, from W bigger than B and just A?
You need to integrate and طبعا just بس انا شرحت لكم only the خلينا نقول the shape that before 0 it's 0 and then between 0 and W it keeps increasing linearly. This is what I did. Like in order to find the values you need to multiply this with this and integrate over W0 to W. For specific W. عشان كده يطلع لك هنا 1 over B. And you need to do integration. يعني basically انت عندك هنا 3 phases or 4 phases. Phase when W is less than 0. The answer is 0. Phase when W exceeds A plus B. Simply لما يصير ما في أي overlap between this after shifting, after flipping and shifting and this. هذه واضحة. 2 phases اليمين واليسار. الآن في النص عندك 3 phases. You need to first of all you need to know that there are 3 phases. واحد increasing, واحد constant, واحد decreasing. And then you need for every phase, in order to find the value, you need to multiply and integrate. واضح? Integrate means find the area and the vector. Of course. يعني زي ما قلنا احنا this is not an exam, even in 207. Of course, if there is anything related to Laplace transform, طبعا the complicated ones, the easy ones, you should be able to find. Then Laplace is very simple, integral, right? It's the integral of chemical EDF of x e to minus s x d x from minus infinity to infinity, right? So if this function is easy, you need to be able to find it. It is خلينا نقول من الاشياء السهله في الانتجريت. لكن if it is complicated, you need to give you. So if we don't give you, معناها you don't expect something that you don't. If it is a simple integral, you should be able. واضح؟ أي سؤال ثاني شباب؟ طيب الآن okay. Now if you have 3 functions, 3 random values. So y here equals x1 plus x2 plus x. And x1, x2, and x3 are independent. Then in order to find the PDF of y, you need to have m convolution. One convolved with another, convolved with. So 3 functions you need to convolve. Okay, again, this is the PDF of the sum. So this is one random value, which is the sum of the. بينما هنا this is the PDF of the joint PDF of the three, which is the product. That's the PDF of the sum, which is a PDF of one random value. It's only a function of the of y, for example. بينما هنا it's a function of 3. Right? Now imagine that you have 4 random values. You have how many convolutions? 3 convolutions. Okay, and so on. So imagine every time you have more than the values added together, you will end up with more and more convolutions, which complicates the analysis and makes it extremely difficult to find Okay. Now, there is luckily in general in physics in physical world, you have many places where basically many signals are added together, and you need to deal with the resulting section. One very important example is the noise. The noise in communications or electronic circuits come from noise added at resistor, another resistor, op-amp, filter, and so on. So basically, you have all these electronic devices where basically from the effect of the heat, the electrons move in a certain way, and there will be some noise dissipated across the circuit. So the noise will be a function of noise coming from one circuit plus the noise coming from another circuit, from the noise coming from a filter, from a noise coming from an op-amp, from a noise coming from an oscillator. So imagine how many systems are basically between a transmitter and a receiver. When your mobile operates and you talk or send something until it goes to the base station, it is received and goes to the next user. So imagine how many systems, how many subsystems there exist, and every one of them will introduce its own noise. So how many combinations you need to do to find the PDA of the noise? Right? Which is, doesn't make sense. So in general, if you have sum of n random variables, you need n-1 combinations, which doesn't make sense. And this leads us to what we call the central limit theorem. Central limit theorem is a theorem, well-established theorem in quality, that says the following. If you have a sum of large number of independent random variables, okay, large number, 100, 15, 20, whatever, of independent random variables means what? Independent means what? Every one of them comes from a source independent from the other. واحد جاي من oscillator, واحد جاي من filter, واحد جاي من op-amp, and so on. Subsystems. So in this case, the probability distribution function, which is the CDF, of the sum will approach Gaussian distribution. We're going to do n-1 combinations. If you have a sum of large number of independent random variables, the result will be the CDF will approach the CDF of Gaussian. Okay. There are some. This is a very general result. However, some dependent random variables also apply. It works for equal or unequal distribution. So if these n random variables are all uniform or all exponential, or one of them is uniform, another exponential, a third is Poisson, a fourth is whatever, the binomial, large number of them will give you Gaussian. So whether they are the same or similar or unsimilar distributions. Okay? Works for continuous. And there is another one for even discrete. Practical applications when you have finite in هنتكلم الآن when you have finite in what is the various approaches and how we calculate now the various. Okay. So when we say here it approaches Gaussian. Nobody says it is Gaussian. It approaches means that as the number increases, it becomes closer and closer to a Gaussian. Okay? And because of that, we have the noise in all electric circuits is usually modeled as a Gaussian distribution because it's a sum of large number of independent random variables. Now let's talk about the details. Now, if I have a large number of random variables that are summed together, so what do I have? I have a sum of IID. What does IID? IID is independent and identically distributed. You will see this word in many cases. IID means independent and identically distributed. I is the first I is independent, the second I is identical, and the distributed is the D. Okay? So what do we have here? We have a sum of IID, means that x1, x2, the xn are what? First of all independent, yes. The second is identically distributed. All of them have the same distribution. And we said that there is another version of the simple Hamiltonian even with non-identical. But now we stick here to the identical and independent. There are different versions of the simple Hamiltonian or even dependent and non-identical variables. Some of them will give you also Gaussian. But here we'll only stick at identical and independent and identical distributed. So here we have yn, which is a sum of n random variables. Because of that, we give it n, is x1 plus x2, blah, 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 where these x's are independent from each other and identical. They have the same distribution. Brother? Now, we said that yn will approach h, right? Huh? Gaussian, more important. Gaussian. That's the value. But if it approaches Gaussian random variable, is that called Gaussian H copy? How to describe a Gaussian random variable? Variance we need. If I know the variance and the mean, I know everything about Gaussian. So in order to now, for yn, if it approaches Gaussian, I will be interested in knowing what? The PDF of yn, which means knowing the mean, its mean, and its variance. And this is what we're trying to do. We try to quantify the mean and the variance of yn. Because if we know it, then we know the distribution of yn in Islam. Okay? So identically distributed means all the x's have the same distribution. Means that they have the same mean, but same distribution means same PDF. Which means that the mean is the same, right? And the variance is the same. So the variance of x, the mean of xi is x bar, and the variance of xi is sigma x. The other thing is means that the mean and the variance is the same. Further.
You said that the pyramids equal and unequal.
Yeah, لكن احنا قلنا الان حضرتك في الكلاس for only identically distributed and independent. احنا قلنا there are versions of the simple Hamiltonian or even twice with dependent, not independent, and not identical. But if we fix here to the simplest case, independent and identical. Now, if I have the mean of xi is x bar, the variance of xi is x sigma x squared, then what is the mean of yn? The mean of yn equals what, Shabab? Is the expected value of whatever inside. What is yn? Yeah, it's a summation for I equal 1 to n of xi. So the mean of xi is the mean of the summation. And we know that the expectation operator is a linear operator. Huh? So this is equal to the expectation of x1 plus the expectation of x2 plus the expectation of x3, is it? So this is equal to the summation of the individual expectations. Right? But what is this? What is the expected value of xi? X bar. What is the expected value of x2? X bar. What is the expected value of xt? X bar. So we have how many x bars here? N of them. So we have n x. Okay? So this is the mean of the resulting, the sum of independent random variables, yn. Now, so we know the mean. We need to find the variance. Similarly, we just go with the equation, with the definition. What is the variance of yn? It's the expected value of, what is the variance of yn? It's the expected value of what, by definition? Huh? Yn minus yn bar, exactly. Which is the mean square. But what is the what is the yn? Summation I equal 1 to n of xi, right? Minus what is yn? n x bar. So I can take as if it's a summation of x bar, صح? Isn't it? And I put x bar here. All square. Is it? صح؟ يعني I have n x bar as if I had summation. I just put x bar inside. So this gives me this expected value of summation of xn minus x bar, the whole thing square. So what do I have? I have here a sum multiplied by a sum. But square means multiplied by each other. So what do I have? I have the sum square. What we did here is this. We defined this as x tilde. So we define this as x tilde. Define this as x tilde. Okay? Xn tilde. What is xn tilde? Is xn minus x bar, which is a random value that has, what is the mean of x tilde? What is the mean of this random value? What did I do? I took xn minus x mean. So what is the resulting random variable? What has a mean? What is the value of this? I subtracted the mean. And I need voltage on the DC. I subtracted the DC. What do I get? Huh? 0. I subtracted the average. So what do I get? I get a random variable that has a 0. تذكر بنتكلم زمان عن Gaussian. We said that we go to the normalized Gaussian. What did we do? We subtracted the mean and divided by standard deviation. Anyways, so now what do we have here? We have summation of n random variables squared. So what is the summation? Square is the double summation. Basically, كل item multiplied by each other, basically every item in this summation multiplied by every item in the other summation. So we have double summation of I and j, xi tilde, xj tilde. So how do we go from here to here? We just open double summation. Now what do we have? We have the expectation is a linear operator. So we can take it inside. We can take the summation outside. Expectation is a linear operator. So this is double summation I and j of expected value of xi tilde, xj tilde. But what is this? This has two cases. When I equal j means what? Means we have expected value of xi squared. How many of these I equal j? How many times it happens? 8 times. So basically I goes from 1 to n xi squared. And we have the other cases where I not equal to j, where we have double summation, however, when I not equal to j. In this case, this will be equal to expected value of xi tilde multiplied by expected value of x. We did this because they are independent. I'll tell them chapter 5 and joint moments. This was separated into expected value of xi, xj because they are independent. Because simply the PDF, the blank PDF recovers, also the expectation recovers. But what is this? What is the expected value of xi? Zero. What did we do? We subtracted the mean. So this has zero mean. Xi tilde is zero mean. So this is 0 and this is 0. So the whole thing is 0. What do we have then? I expect the summation of xi tilde squared. But what is this? What is this equal to? What is xi tilde? Xi minus, right? صح? By definition, xi tilde was xi minus x bar. What is this equal to? sigma square. Basically, this is equal to sigma xi square or sigma square because they are the same. Sigma x. So we have here summation of sigma xi, which is n sigma x. Because they are the same. They already have the same values. So now we know that yn, which is the summation of independent and identical distributed eigenvalues, regardless what are these eigenvalues, I don't care. Whether all of them are exponential, all of them are uniform, all of them are Poisson, it doesn't matter. The result is the sum has a distribution of Gaussian with mean equal to n times the average of every one of them, and the variance will be n times the variance of every one, regardless of what are the details of the x1, x2, x3, what is the distribution. So instead of having n minus 1 convolutions, central limit theorem gives you that the answer is the distribution for yn is Gaussian, and here is the mean and the variance. Very powerful. Extremely powerful. Okay? بدنا نسوي convolution لاشياء معقده جدا انت اصلا يمكن مستحيل تقدر تسويها. Central limit theorem gives you an average, it reaches Gaussian and you need to only find the mean and the variance. The mean and variance luckily ما له علاقه بالdistribution. Distribution ممكن يكون exponential, ممكن يكون uniform, ممكن يكون اي شيء. As long as you know the mean and the variance of every one of them, this is the result.
So the higher the number of n, the better approach the result.
It approaches Gaussian in a better way. It becomes more Gaussian. And again, at the end, it approaches Gaussian. It approaches Gaussian. Nobody said that it is Gaussian, but it approaches Gaussian, and they will show you now some experiments about. We'll come back to that. Here we are giving you the uniform distribution. So here we have fx, x and x1 and x2 are IID. All of them are uniform. So we have x1. So the PDF of x looks like this: between 0 and a, 1 over. Okay. This is the same for x1, for x2. Now, when you do this convolution, when you convert this with itself, what do you get? The famous rectangle. Triangle. Oh. When you convert two rect functions, what do you get? Triangle function. Triangle function. And so here we are plotting the triangle function, which is what we found using convolution, fx1 convolved with fx2. Okay, and we are plotting the Gaussian distribution, which is Gaussian distribution, and we found the mean. So this is expected value of y w. ايش رايكم كم expected value حق w؟ تمام. y1. What is the expected value of w? 2 a y. What is the expected value of x? A over 2. It's the middle point. Huh? So what is the expected value of w? So expected value of this is 2 multiplied by a over 2, which is, and you can see it's here. And the variance of w equals what is that? 2 times the variance of x squared, which I think it's a square over 12 also. I'm not sure. Anyway, it is written here, it's a square over 6. Because here you have 2, right? Which is this one. Okay? Now we are putting here the Gaussian and the rectangle triangular. شوف كيف ما هو بعدها. شكل مختلف صح؟ هذا triangular هذا Gaussian لكن they are not far away. الآن let's increase more. So here we are plotting for n equal to where you have rectangle, right? Sorry, triangle. Triangle having less. Here n equal to 3. Here n equal to 2. And you can see the red one is the Gaussian with the mean and the variance according to the equation that we found. The blue one is the convolution, the real convolution. When you convolve uniform twice, sorry, one time uniform with uniform, 3 uniforms for 2 convolutions, 4 uniforms, 3 convolutions. You can see that how close the red one, which is the Gaussian, with the blue one, which is the convolution. So you don't need 100, n equal 100 to get the Gaussian. Usually n equal 10 or 8 or so, most likely you give the Gaussians. You can see here from 4 we are very close, except for here and يعني تغييرات in the tail عادة التيل والسنتر يكون كبير. بس بصفة عامة you are very close.
طلع عندنا definition for 2. Standard is the triangle, right?
إيه.
عندنا function يعني other function. يطلع عندنا definition square.
لا آخر شيء هذه هي الفكرة. راح يكون بعيد مرة. It will converge to Gaussian. They converge to Gaussian. That's أي شيء. Okay, ممكن الاثنين حيكون بعيد لكن لما when you convolve 5 of them, 6 of them, you will find that it will approach Gaussian. زي ما قلنا very powerful شيء يعني عجيب.
هي دي كلهم نفس نفس الدستور نفس كل حاجه كلهم
نفس الديستريبيوشن مع نفس المين نفس ده. الديستريبيوشن is a PDF. إذا الPDF نفسها فهناخد شو نفس الشيء صح؟ المين البيانات كل المونس هذا اسمه.
النوع الثاني. السيت كم يعني عادي عندنا يعني كل المونس.
كل ريزستور كل كاباستور كل ترانزستور كل يعني if you go to the component level كل واحدة تطلع. If you go to subsystems كل فلتر كل بس فلتر كل واحد يطلع.
معين عندهم مواصفات جاسم.
زي ما قلنا 4 5 10 نوع جاسم. So in the communication system you have many of these, hundreds of these. So definitely it's Gaussian. Here experiment here shows you that you don't need to go to large N 100 until you reach Gaussian. The experiment here shows you that for uniform, very simple. 4 was almost enough. 5 is enough to get you almost Gaussian.
Usually these noises are not identical.
They are usually no. ممكن يكون بعضهم right. طبعا أنا قلت لك في stronger version of the second machine where basically it applies to dependent and non-identical. اللي احنا اتكلمنا هنا بس only symbols. And we did not prove it. We only did it. لكن in general it gets more convolutional styles. هاي شنو؟ واضح؟ طيب بس نرجع للسلايد اللي عندنا. Yeah. Now if I give you the table of the Gaussian, yeah, and I tell you that the Gaussian is we have 10 exponential random variables or 100 exponential random variables added together. They are IID, independent, and identical. And I ask you, and I give you that yn equals the summation of these exponential random variables, also whatever. And I tell you what is the probability that yn is less than 1. So what is yn in this case? الآن جالس أقول لكم مثلا عندي xi xi are i's are certain random variables with certain distribution. I random variables with certain distribution. Certain with certain distribution. Okay. Now, yn equals the summation of I equal to x. Okay. The question is find the probability of yn less than 5. How to find it? So I set the distribution. I give you here the details. I've taken the meaning values. I didn't come with a problem. With certain distribution such that with expected value of x I equals x bar and sigma x I equals sigma. أعطيت فيها أرقام معينة ما تفرق. خلاص؟ find the probability that yn is this time. How to find? Okay, so what is this equal to? Normalized, huh? This is equal to what? F table, huh? Of what? 5 minus 10. The average of what? yn, صح؟ صح؟ No? It's the average of yn. صح؟ Divided by what? Sigma what? sigma yn. صح؟ الآن أنت عندك التابل وعندك الفايل. You need to find this and this. So what is yn average? It's n x bar. And what is sigma yn squared? N sigma x squared. So you just plug it in. If you notice here, it's sigma yn. That's sigma yn. Okay. So any problem like this, you need to be able to find it. And here, what I did is we defined what we call normalized Gaussian random. مثل ما سوينا. Normalized Gaussian sum, where basically you take yn, subtract from it the average of yn, divide by standard deviation of yn. And when you do this, it will be summation of this xi minus xi bar divided by the standard deviation, which is square root of the summation of the. Now, when you open up this, it will be 1 over square root of n sigma x summation. Very similar to what I did. Now, the good thing about this is that this normalized Gaussian sum has a 0 mean, and a unit variance. So what is this? This is equal to W. This is W. So Wn equals Yn. So here Wn equals Yn minus Nx divided by sigma x square which is the standard deviation y. Okay? So this has now Wn has 0 mean and unit, semi-unit variance, right? Variance. It's a normalized sum. Sum can yn.
has certainly an x bar وفاريانس n sigma x.
ايش عشان الان اوجد اي شيء related to yn I need to find the normalized, which is اللي سويناه اللي هو you subtract and so basically what is this? What's wn? wn here is yn minus its mean divided by its sigma square, its standard deviation. Now wn here is normal نتذكر هذه with zero mean and univariance. Normal distributed with zero mean and univariance. Again, is normal with zero mean and univariance. So our quiz will be next Sunday, right? By this we completed chapter 4. Chapter 4 was, as I mentioned, was about 2 or more variable values, describing the need for these variable values, the different situations they describe, and then how to describe these variable values using the don't PDF, the don't CDF. And then we talked about the marginal PDF in continuous cases. And we talked about conditional distribution as basic functions in half-point conditioning or interval conditioning. And then we talked about the summation or finding the distribution of the sum of individual values. We defined independence before that. And then we ended up with the simple theorem, which gave us a very powerful tool to find the distribution of the sum of IID values. As Gaussian, we were able to find the mean and the variance in order to plug in using the table of Gaussian. This concludes chapter 4. Next time, shall continue with chapter 5. Any questions? See you inshallah next Thursday. Thank you.